Vectors! So what is this vector? What is a scalar vector? It is any quantity that has both a magnitude and a direction. A magnitude is the size of the quantity, how big the quantity is. Direction is which direction it's pointed in. So if you can represent a quantity by drawing an arrow on a diagram, chances are you're drawing a vector. So the length of that arrow will be the magnitude, the direction is going to be the direction. Scalars only have a magnitude, so something like 10 kilograms mass is an amount, it's only got a magnitude, so it's a scalar. So in one dimension it's very easy. You just take the algebraic sum of these two forces. I'm applying a force of about 100 newtons in the positive direction. My student is applying 100 newtons in his direction, the negative direction. The algebraic sum of these two forces will be 0. So the system, you can see, is stationary. However, if my student starts to apply a greater force in his direction, then the system will start to move and accelerate towards him. Addition of vectors in two dimensions is a little bit more tricky, but we can visualize it like this. If we track the displacement of a snowball using displacement vectors, the snowball first travels from A to B along a straight path. That's our first vector. And if we were to add it to a second vector, which travels from B to C, we would see that the resultant displacement, the total displacement of that snowball, would be from A to C. So here we have one of my students who forgot their homework, and he's in equilibrium, which means that these three forces all balance each other out. But how do we show that? Again, we have to move these vectors around so that they line up head to tail. And when we do this, they form a beautiful arrangement called a vector triangle, where if you follow the path of the arrows, you end up at the same original position, which tells us there is 0 net force, and the system is in fact in equilibrium. Now that might seem obvious to you now, but one of the most common mistakes that students make is when they're trying to find the resultant direction and magnitude of two perpendicular forces acting on a single object. Finding the magnitude is easy. Because these two forces are perpendicular, we have a right angle triangle, and Pythagoras' theorem tells us that the square of the hypotenuse is equal to the sum of the squares of the other two sides. The mistake occurs when trying to find the direction of this resultant force. Because we're already thinking in terms of triangles, it's very easy just to connect the end of both of these two vectors and stick an arrow in the end. But of course we have to shift one of the vectors so that its tail lines up with the head of the other vector, and then our resultant direction will be from the very start of our train to the very end. Okay, so here we have a vector that's inclined, let's say 30 degrees to the horizontal. What we need to do is we need to split it into its horizontal and its vertical components. So we just make a right angle triangle where the bottom length is our horizontal vector and the side length is a vertical component of that vector. And we have an angle theta, let's say it's 30 degrees. Because it's a right angle triangle and we know one of the angles, the opposite side is the opposite. This side is the adjacent, and the longest side, our original vector, is going to be the hypotenuse. So if we know what the hypotenuse is, we can calculate, using our angle, we can calculate the opposite and the adjacent side. So you know that the sine of our angle is equal to the opposite over the hypotenuse, and the cosine of that angle is equal to the adjacent over the hypotenuse. So if we want to find that horizontal component, we would use this formula. So our adjacent component is just equal to the hypotenuse, the length of the hypotenuse, multiplied by the cosine of our angle. And if we want to find the vertical component, we would say that the opposite side, the length of the opposite side, is equal again to the hypotenuse multiplied by the sine of that angle. So a common application of this is you have a point mass on an inclined plane, and that point mass has some weight which acts vertically downwards, that weight is mg, and the plane is inclined some angle alpha to the horizontal. And you're being asked to find what are the components of that weight which act parallel down the slope and what components of that weight act perpendicularly up. What I'm going to do is I'm going to make another right angle triangle. And the right angle triangle is like this. I need to find the angle, like so, such that the perpendicular component of our weight and the slope itself are at right angles to each other. And so this angle here is going to be our angle alpha. That's a little bit small, but maybe you can read that. So that's just like having a point mass which is being subjected to two independent forces. One of them is acting in this direction, the other one is acting parallel to the slope, down like this, and the resultant of these two forces is our weight vector. So if I were to add this force and this force, it would give me the weight vertically downwards. This is mg. And because we have this triangle here, we're going to draw that triangle again. And this is our right angle. This now is our hypotenuse. This is our angle alpha. So this is the opposite side, and this is our adjacent side. If we want to find the parallel component, that's our opposite, we would use length of that opposite is equal to the hypotenuse, or mg, multiplied by sine alpha, and our adjacent side is going to be equal to the hypotenuse multiplied by cosine alpha, and that's true for most cases. So where we have to find the parallel component of that weight, it's always sine of alpha. Where we have to find the perpendicular component of that weight, maybe we're trying to find the normal contact force, or we're trying to find the friction that this point mass will be subjected to, we would use cosine of alpha.
At my back, yeah? At my back. Not at my butt!
It's not right.
Cool. Okay, in the last video we saw how we can separate these two types of quantities. Separate these two quantities in terms of whether they are a scalar. That's the pause part, so that's where somebody comes in and writes scalar on the board. Can somebody do that?
5 1?
So, and the pen.
Component acting vert. No, I'm going to start that again.
Yeah.
Your face said it all, John.